Well, welcome to Lesson 3.2 on Exponential and Logistic Modeling. In this section, we are going to look at some of the exponential and logistic equations that we've been working with and use those to solve real-world problems. So we'll start out our lesson talking about population problems that are constant growth rates, and each of these functions we'll have the form P of t, or our population, our function is equal to a b to the x. That's our standard form for our exponential growth and decay. And if our b factor, if our base right here, remember if that's greater than 1, then we have an exponential growth function. If that is less than 1, we have an exponential decay. And a is our initial value. So let's suppose we have the population of Mankato in 1875 being 3,482. And I actually looked this up on internet, and that's an accurate number. And we're assuming that the population is going to increase at a rate of about 4.5%. And that's pretty close. It's a little bit high, but that's close to what the growth rate was. So the first thing we want to do is to write an exponential model for the population of Mankato. And so our initial value is 3,482. That is the a in our equation up here. And our growth factor, this b, is 1 plus the rate as a decimal, so that's going to be 1.045. So our function p of t is 3,482 times 1.045 to the x. The second part is to determine the population in 1885. Well, that's just 10 years after our initial value, so we are going to find the population when our time factor is 10. So P of 10 is equal to 3,482 times 1.045 to the 10th power, and if you plug that into your calculator, you get 5,407. The last part of the question says determine when the population is triple the original amount. Well, if we multiply our initial value times 3, we get 10,446. And what we can do to this is we can just plug the right-hand side here, this 3,482 times 1.045 to the x power, into our y1 value in your calculator, and then plug in 10,446 into the y2 value, and go ahead and calculate the intersection point. And it looks like our intersection is at 24.96. So we're going to say that that happens at approximately 25 years later. All right, our next problem says it's an exponential decay and half-life problem. Suppose we have a radioactive substance, and we're told that the half-life of that substance is 20 days. Now, what that means is it takes 20 days for your initial sample to decay to be half of that. So the problem says express the amount of substance remaining as an exponential function of time. So the amount that would remain, again, we're going to have our basic function. Our initial amount was 10 grams, and we need to deal with this 20 days in here yet. We need to find what our decay factor is here. So we're going to go ahead and plug in the point 20, 5. That says that after 20 days, we only have 5 grams. The 5 grams comes from half of 10, so that's where the half-life comes from. So if we plug this point into our equation, plugging 20 in for x and 5 in for y, we get 5 equals 10 times b to the 20. And we want to solve this for b to find what our decay factor is. So if we divide both sides by 10, we get 1/2 is equal to b to the 20th. That's in blue. And then if we raise the right-hand side here to the 1/20th power, this will give us b to the first power. But whatever we do to one side, we must do to the other side. So we get 1/2 to the 1/20th. So now we know that our decay factor is 1/2 to the 1/20th power. So now we can plug that back in over here to this y equals 10 times b to the x, but replace b. So we get y equals 10 times 1/2 to the x over 20. So if we raise that to the x power, multiplying this to the x power, we would get x over 20. So that's where that comes from, and that is actually our equation. Part B says find the time when there will be 1 gram of substance remaining. Well, what we want to do there is we want to actually find when y is equal to 1, when is this output 1? So you could put the right-hand side into your calculator for y1. For y2, just plug in y equals 1. And that's what I've done down here and found the intersection point. And it looks like that happens at about 66.4 days. So roughly 66 days we have 1 gram of that material remaining. Here's a logistic model. It says find a logistic equation of the form that's given that fits the graph if the y-intercept is 5 and the point 24, 135 is on the curve. Well, the y-intercept is our initial value, right? So when x is 0, y is 5. And so we're going to plug that in and calculate what we're going to get for our a value here, for our initial value. So we have 5 is equal to c over 1 plus a e to the 0 power. And anything to the 0 power is 1. So we'll just get 1 plus a on the bottom. And we also know by looking at the graph, we're going to level off at 500. That's going to be our maximum value. So let's go ahead and plug those pieces of information in. We get 5 is equal to 500 over 1 plus a. Well, to solve this, we could put the 5 over 1 and cross multiply. And we'll get 5 times 1 plus a, and that ends up giving us a value of a equals 99. So now we can plug that back into our original equation. Y equals c is 500, a is 99, so here's our equation. Well, we still don't know what b is, so that's a problem. We need to figure that out yet, and we have not yet used the point 24, 135. So let's go ahead and plug that in. If we plug in 135 as an output value, and then we have the same thing for our right-hand side, and then we're letting x be 24. So now what we can do is we can plug in y1 in our calculator as 135, y2 is the right-hand side, and find the intersection point. And it turns out that those two graphs intersect when x is 0.1500. So now we have the final equation is, and I didn't write this on here, I should write this really quick for you. So we're going to have y is equal to 500 divided by 1 plus 99 times e to the minus 0.15x. And that is what our exponential, or excuse me, our logistic growth function looks like. And our last slide here, it says Washington High School has 1,200 students. Suppose a group of students start a rumor, and it's going to follow a logistic growth pattern based on this function given here. And that models the number of students who have heard the rumor by the end of day t. How many students have heard the rumor by the end of day 0? So if we plug in 0 for t, remember anything to the 0 power is 1, we get 1,200 divided by 1 plus 39, which is 1,200 divided by 40, which is 30. So by the end of the very first day, or day 0, 30 students have heard the rumor. The next question says, how long does it take for 1,000 students to hear the rumor? Well, we're just going to plug in 1,000 for our output value and calculate what that's going to be. Well, this is a problem we can do on our calculator. Let's let y1 be the 1,000 value and y2 be the right-hand side. And then if we just calculate the intersection point, we see that they intersect when x is 5.86 roughly. So near the end of the 5th day, or almost 6 days, 1,000 students will have heard that rumor. That'll do it for this lesson. See you next time.